Okay. Hey, happy Friday, everyone. Today is August 5th, and this is episode 22 of our Google Hangouts and podcast and all things DOCSIS. I'm Brady Volpe, founder of the Volpe firm and Nimble This. Today, again with us, we have the diviner of DOCSIS, the one and only John Downey, CMTS technical leader at Cisco Systems. John, great to have you back with us today.
Oh, great to be back. Sorry, running late. Technical difficulties. Layer one problem.
Yeah, other problems, all right. So we've got a great show today. We're going to be talking about the top reasons cable modems are not getting the expected speeds in CMTSs. But first, John, I know you're traveling recently, and we also had an Angacom trip that we were at. How was your Angacom trip, John?
It was in Cologne, Germany. It was good.
Any traveling?
Started out. Let's start off with. I could probably write a book now on how to survive in Germany without any money or credit cards whatsoever.
You did a pretty good job at that.
Help from your friends,
right? Yeah, good. Friends are good. And then you had Cisco Live you were at just recently, right?
Yeah. Cisco Live was in Las Vegas, and we had upwards of 28,000 people in attendance at Cisco Live. So it was pretty impressive.
Awesome
a lot of good stuff. But
yeah,
I mean, it's not your typical cable type of show, right? It's Cisco routing, switching, security, everything you can think of. And cable's a small part of it, but we had 2 or 3 sessions on the CBR8, DOCSIS 3.1, troubleshooting, CMTSs. So it was good, a good turnout.
Yeah, excellent. So yesterday I was presenting at the SCTE North Country chapter in Minnesota on DOCSIS 3.1 and PNM, of course. I want to give a shout out to those guys, especially Mark Daniels and David Haig for inviting me and just being excellent hosts while I was there. I did want to share just one slide that I presented when I was giving my presentation, and it's this slide here. For those of you that are watching or just listening to the podcast later on after the live presentation, what I'm showing on the screen is a screen capture that was taken using a DOCSIS 3.0 modem, actually a full band capture modem of the local Comcast feed that is distributing a DOCSIS 3.1 channel. And so it's, I gave this during my presentation, and basically what we're showing on here is a 96 megahertz DOCSIS 3.1 channel that's in the Atlanta area where I'm based. And we show a couple of nice things that you can see here. First of all, that you can see a DOCSIS 3.1 channel using a DOCSIS 3.0 full band capture capable modem. You can see the pilots. And so on this slide, I'm showing the pilots. They're elevated about 6 dB higher than the average channel power of the DOCSIS 3.1 channel. And then you can also see the PLC, and the PLC is the PHY-link channel. We often say that the PLC is really a very critical part of the DOCSIS 3.1 channel, because that's giving a lot of important information to the cable modems, information about how they're going to communicate on the network itself. So placement of the PLC is really important, because if that gets wiped out by like LTE ingress or something in a downstream, all your modems are going to go, all your 3.1 modems are going to go offline. So I have that indicated on here.
Partial mode.
Yeah, exactly. They're going to fall back into a different mode.
Yeah, I think what most systems are going to do right for the start is you're going to have a lot of 3.0 spectrum and 3.1 spectrum, and you're going to cross bond, right? The 3.1 modem is going to cross bond between the single carrier QAMs and the OFDM channel, because no one's really going to have enough spectrum just for 3.1 modems. So they'll cross bond, and if you lose that PLC and lose the OFDM DOCSIS 3.1 channel, you could drop down to almost like a 3.0 mode, like a partial downstream mode.
Right. So Yeah, I mean it's just good to see that we do have DOCSIS 3.1 in production, definitely in the Atlanta area, and also we can see it with DOCSIS 3.0 modems and do analysis of it. We can see the channel power. So there's a little pop-up on the screen here showing that channel 110, 711 megahertz is where the PLC is located. You can measure the channel power there. Now, the one thing you can't measure is the MER, because MER is measured on a subcarrier basis for DOCSIS 3.1 channels. So unfortunately, you can't measure that with a DOCSIS 3.0 modem. So that's something kind of cool to look at. I don't know if, John, if there's anything else you want to discuss on 3.1 on like kind of the downstream here.
I actually have I have a question for Brady. Did we rename, because full bandwidth capture really is a Broadcom name, right? Is it renamed generically band capture now?
No, so we went back and forth within the PNM working group. At first, we thought we had to get away from full band capture because that was something that Broadcom came up with, but it was not trademarked, and Broadcom was okay with us using that kind of as an industry term for full band capture, just because it's been so widely used and so widely adopted across the industry. So it's something that's generally accepted. You can use that as whether it's an Intel-based chipset or a Broadcom-based chipset is something we can use.
Okay, I mean, is the other term wideband capture basically synonymous?
Yeah, wideband capture, full band capture, they're all synonymous. So
okay. Yeah, I mean, this is good. I mean, we even did a little bit of testing ourselves with the 96 and 192 megahertz OFDM channel, and I was pleasantly surprised at the robustness when we injected carriers right underneath of my OFDM block. And I believe it's not just because of interleaving in the time domain, but possibly interleaving in the frequency domain. You're interleaving across subcarriers. It's more PC, better FEC. It just surprised me with if I had narrow ingress, and it could be even 6 megahertz ingress, maybe it's LTE or an off-air broadcaster, and the level of MER I reached in 4K QAM would still work, meaning that it wasn't a low MER for all my subcarriers, but a subset of subcarriers. Like, let's for instance say my channel at only 6 megahertz, you know, that would be, say, 50 kilohertz subcarriers. That would be whatever that number would be, like 100 subcarriers, whatever it is. Let's say the MER is down to like 20. A 20, you know, you wouldn't even think 64 QAM would work. Maybe I'm stretching it a bit. But if the rest of the subcarriers were, say, 35, 40 dB, I could get 4K QAM to still work without uncorrectable FEC, which almost makes it look like you were bypassing some of the subcarriers. But because of the interleaving and the FEC and LDPC and all this other stuff, I was pleasantly surprised at how robust it really was. In regards to the PLC, you mentioned, yeah, you want to definitely place it in a nice, clean portion of your spectrum, but it's also running 16 QAM, so it is like pretty robust in that regard as well, right?
Yeah, yeah. So not only is it running 16 QAM, but it has the LDPC error correction, which is much more robust than a Reed-Solomon error correction. So it is going to be very resilient to any type of ingress we would see, and even in the downstream, the ingress that we typically see isn't like the ingress that we see in the upstream.
Correct. I think as we see this mature, we're going to see some best practices, some more recommendations. Maybe we can ease up on our conservative approach to some of our thresholds. Like from the very beginning, we've all said that, oh yeah, in today's plane where you run 256 QAM, you can run 1K QAM, no problem. I think a lot of systems are saying, well, 2K QAM is probably going to be okay for most of my modems. Look at my MERs. I'm almost leaning towards 4K QAM is going to be good for quite a few modems too. And that's where I think we need to be proactive to see the MER readings of all the subcarriers and monitor over time, and have SDN app or some type of application that looks at all the modems, all the MERs of all the subcarriers, and then dynamically moves the modems between profiles.
Yep, absolutely. All right. So, John, today back on to our topic. I think you also have some slides to talk about DOCSIS upstream and downstream speeds, right?
Yep. So do I just start? Do I just share it from my slides?
Yeah, share directly from your slides. Upper left-hand corner, there's that little green share button.
All right. Let's see. I'm looking for the little green button. I guess I should have prepared for this one. And so click on my slides. I see a WebEx share this file.
Not on your slides. It's screen share on the Hangout there.
Okay. I think I see it. There we go. Let's do this. So you see that?
Yes.
Okay, let me hide that. All right, so I think you and I kind of confirmed that we don't think the slideshow presentation works in this, right?
No, it doesn't very well. Yeah, so that's one of the limitations of Google Hangouts. Full presentation mode doesn't work. So one of the things we have to do is just you guys are all going to see the raw slide deck in here. So it's one of the limitations.
I can zoom in a little bit better.
That looks fine, John.
Looks good like that? All right.
It looks good.
So I mean, I threw these slides together based on some other presentations I've had over the years on understanding throughput and trying to get the best speed possible. And I said, if we just look at the OSI, the 7-layer OSI model, starting at layer 1, work through layer 2, 3, and 4. Why do people not get the speed they're trying to get? Like, what is the pitfalls? What's holding me back? And a lot of it is like user error or self-inflicted pain when trying to do certain tests, like you're trying to do per modem speed tests. Upstream and downstream totally different. Whether you're doing UDP or TCP at layer 4, that could have a definitely reaction to your speed test and results. So my agenda was looking at troubleshooting, just starting out troubleshooting, looking at the OSI model, my rules for capacity planning, things that I can do to increase it in some potential issues. To go through this kind of quick, the 7-layer OSI model, I have my own Johnny mnemonic here. My mnemonic, and these have been thrown around quite a bit, is all people seem to need data packets, or please do not throw sausage pizza away. So whichever way you memorize this 7-layer model, so be it. I don't really care. But anytime you do troubleshooting, always start at layer 1. I have a lot of IP guys that are layer 3 centric, and they'll start looking at the router and switches and SNMP and layer 3 information when, why don't we just make sure things are plugged in and the dummy lights are on? Let's always start layer 1 and work our ways up from there, especially when we're doing speed tests. You got to make sure you're not having uncorrectable FEC, drop packets, and all your settings are actually set properly. Your MER readings are good. So then I came up with, looking at the OSI model, a little bit of humor here. I made up a haiku. Faulty layer 1, but check layer 2 before, layers 3 and 4. So that's my haiku. Looking at, I'm not trying to be a poet, but hey, what the heck? It's my slide.
Yeah, I wouldn't quit your day job on that one. So.
So it's no fun with faulty layer 1. So we start at layer 1. We look at drop packets. We looked at testing through wireless. Well, anytime you don't do it through a wire and you're doing through wireless, there's other encapsulation happening. There's other, people don't think about ingress at wireless, 2.4 gigahertz. You could have ingress and overload from other wireless devices or even your microwave for that matter. Hopefully your microwave's not leaking, but hey. VPN, that could add 50 or so bytes of encapsulation to all your frames. Gig port, if you are wired, the gig port itself is limited to about 960 to 970 megabits per second. So you'll never really get 1 gig of speed in your customer's eyes from a gig port. So these new modems, DOCSIS 3.1 modems, usually have multiple gig ports. So if you're trying to do more than 1 gig from a single PC with a gig Ethernet cable, you're not going to get gig. You're going to get about 960. The second part, don't be blue, proceed to layer 2. Layer 2 Ethernet, you got to realize that if you're going to do a test, always do it with the biggest frame possible. If the small frames are 64-byte frames all the way up to 1518, DOCSIS, right from the very beginning in the spec, indicated 1522 to allocate a 4-byte VLAN tag. But DOCSIS 3.1 actually increased that to 2,000 byte PDU, payload data unit, or MTU. So that's 2,000 bytes. If I could do that, 18 bytes of overhead on 2,000 bytes is not that much overhead. But 18 bytes of overhead on a 64-byte frame, that's quite a bit of overhead. So if I can do, go ahead.
So what is the actual setting there? So I always thought it was like 15, 18 bytes, but then you see the MTU size on the CMTS is typically 1,500 bytes. So I do get confused in what the actual correct setting should be for the MTU size to be optimal.
It gets very confusing between CMTS, test equipment that is a traffic generator, because you'll see it'll say full MTU including overhead. So it could be 1518. Another time it might say the biggest frame you should do is 1514 because there's 4 bytes for the CRC. Does that sound right? Or is it 2 bytes? 4 bytes? 6642. Or is it 4? Yeah, I'm confusing myself as well.
Yeah, keep going.
So a lot, and sometimes the testing says don't include the 18-byte Ethernet overhead because it'll be added in. So the biggest frame you should do is 1500. So it does get confusing, and I've seen different equipment require different things, and that's when you say, go read the manual. You'll be safe. I guess you could say you'd be safest doing a 1500 byte because then you'd be small enough not to be a jumbo frame. So if it doesn't include the 18 gets thrown in, you're at 1518. What I've done with speed tests is I try 1518, I've tried 1500, and I kind of manipulate the number till I find the best number that works well, or it doesn't cause any problems.
Yeah, so that's actually what I end up doing is I run a speed test and then I change the MTU size. If the speed test gets better, I change a little smaller. If the speed test gets even better, and this of course is one of the recommendation is always make sure you're using a local speed test server, one that's in the head end, same as the CMTS or the device that you're optimizing.
Correct. I mean, you don't want to throw in another variable by going outside of the head end to some website you have no idea or control over.
Right.
And that brings up another point. A lot of speed test sites, you can't control the Ethernet frame size you're testing with anyway. You just hit go.
Yep.
And a lot of times I found out those end up being a 1024 by Ethernet frame, which may have not been as optimum as, say, testing with a 1500 by Ethernet frame.
Right.
I said it's hard to see past layer 3, but don't ignore layer 4. So, I mean, layer 3, the traffic generator itself, is it doing IPv6, IPv4? Is there extra overhead there? When we do reporting, like your end customer is looking at their speed test results, they're usually including at their layer 3 and above. So it's not including the layer 2 18-byte overhead. So when I look at my CMTS counters and my cable modem counters, it could say 1 gigabit per second, but the end customer might see 920 megabits per second because they're eliminating those 18 bytes of overhead on every Ethernet frame. And if those Ethernet frames are small, then that percentage is kind of big. So it could be anywhere between 1 to 10% overhead and not even realize it. Don't ignore layer 4, meaning if I'm looking at the best possible way of testing, you should be doing UDP, user datagram protocol, which is individual upstream or downstream independent. TCP is a two-way street. If you're doing transmission control protocol, the downstream, FTP, downloading a file, you have to have upstream acknowledgments before the TCP flow can keep sending downstream traffic. Typically, we see 2 downstream frames for 1 upstream acknowledgement. So we do all that math, you turn out the upstream throughput could be limiting your downstream testing. So the upstream could be the bottleneck of your downstream test. So to avoid that or get rid of that variable, just do UDP testing if possible. But some test equipment, traffic generators might not have that option. So layer 1, understand your MER, CNR, correctable, uncorrectable effect, understand modem levels and ranging, when the modems are coming online, T3, T4 timeouts, look at the modem flap list. It now might be called modem diagnostic log. You can do layer 3 ping versus a layer 1, 2 DOCSIS ping just to prove the modem is actually online and getting layer 3. You have upstream spectrum monitoring in the CMTS. You have proactive network maintenance. for pre-queue information, and the wideband or full bandwidth capture for downstream spectrum analysis. So start layer 1, physical layer. I mean, it doesn't really end there. You still have to make sure your modems are in the proper state. So this is a big one that comes up with me lately, is that people think their modems are doing 24/8, meaning 24 downstream, 8 upstream, or 24/4, or 16/4, or whatever. But they don't realize that just because the modem is reporting physical channels of downstream and upstream doesn't mean the service flow is using that bonding group. So you could have a case where the modem is reporting 24/4, and then you don't realize that all voice calls in the upstream never get bonded. They actually use a single channel bonding group, if that makes sense. Single channel bonding sounds like an oxymoron. So single channel means when you have a scheduled flow on the upstream, we're not going to spread it across multiple upstreams, because then you couldn't guarantee the jitter and latency. So they are pushed to a single scheduler in one upstream channel. So
now that's a function in the CMTS, right? Or is that a function of QoS, where if you do a voice call, the CMTS recognizes this is a voice call? And I mean, who actually decides that? Is it the CMTS that decides that, or is it packet
it's the CMTS. So the CMTS would see that it's a scheduled call and have to schedule it in the upstream scheduler for mini slots, and then it would assign it to one of the default single channel bonding groups. So even though you might have made a 4-channel upstream bonding group, your best effort data, like surfing the net and whatever upstream traffic, would be 4-channel bonding, but your voice calls, if they are UGS, would end up using a single channel.
Okay, so
I bring it up because you could have a case where a modem shows as UB upstream bonding, so you think it's doing your statically manually created 4-channel bonding group, but it shows UB because it picked a single channel bonding group. And then you're like, well, why am I not getting the speed? Well, it's only doing single channel. You're not going to get better than probably 10 to 15 megabits per second. It might be still doing FTC mode or CCF, continuous concatenation fragmentation, so which will get better per modem speeds. But if it's only doing single channel, what do you expect? A single channel is only worth about 27 megabits per second, and doing a single modem test on one channel, maybe you'll get 15, depending on settings. Does that make sense?
yeah, absolutely, absolutely.
So my point is, I've seen modems that show 8x4, and in the configuration in the CMTS, you may have configured 2 4-channel bonding groups embedded in the 8-channel bonding group, and it turned out the modem picked a 4-channel bonding group for the best ever flow and the other 4-channel bonding group for some other flow, and then it showed up as 8 channels, but it wasn't doing 8-channel bonding. So I need to make sure my service flow is actually using the proper forwarding interface.
Yeah, but in that case, isn't the cable modem if in a DOCSIS 2.0 mode as you're indicating, and it would show that? It would show online versus W online?
That's the first bullet point. That's if I have a 3.0 modem that comes up as online mode, then it's basically 2.0 mode. That's an easy one to follow, but you still have to be proactive enough to know what command to run to find out which modems are in that mode. There's like a command, show kill modem wideband register traditional DOCSIS. That's a Cisco command. You could track that. I would recommend tracking it every day and making sure that if modems are 3.0 modems and they're in 2.0 mode, maybe clear them out every day or figure out why. The point about the service flow was bullet point number 3. That was just making sure that the modem, even though it's showing up as W online, it's not partial, it's W online, and it's showing, say, 8x4 mode, it doesn't mean the service flow is actually using 8-channel bonding.
Right, okay.
I might have to look deeper. And it might be you do the speed test and you don't get the speed you think you should, then you would look deeper. Does that make sense?
Yep, absolutely.
And then other bottlenecks, your CMTS, stale service flows, supervisor, line card, CPU, and memory, SID space depletion. So there's other things that could be depleting or affecting my speed.
So, we used to see SID space depletion occur a lot with DOCSIS 2.0 CMTSs. Or do we still have that occur with 3.0 CMTSs where we have so many more, the SID space increased so much more dramatically?
You know, that one there is kind of interesting because when I look at capacity planning, I'm finding that we have less modems on a CMTS to offer the speeds we're trying to offer. So it might be you're adding more downstream and upstream spectrum and channels to offer higher speeds, but your modem count is still under 40,000 or 50,000 devices. Where I was seeing SID space depletion was when I started doing so many devices because I was offering DSG. DSG, DOCSIS Set-Top Gateway, every house could turn into 3 revenue-generating units, 3 RGUs. I think that's what you call it, right? RGUs?
Yeah.
Because now you could have a house with 1 modem for data and 2 modems embedded in set-top boxes for video. So now that one, say you had a CMTS with 15,000 devices. After you introduce DSG, that could turn out to be 45,000 devices in a couple weeks, if assuming every house gets 2 DSG set-top boxes. So those devices take up SID space, but they don't take up speed. So utilization wasn't my problem, but they do take up SID space. And then you might say, well, what about DOCSIS 3.0 modems? Well, DOCSIS 3.0 modems, to get better upstream speed from a 3.0 modem, we might turn on something called SID cluster 2, which allows a 3.0 modem to use 2 SIDs for upstream bonded traffic. So now that 3.0 modem really looks like 2 modems in regards to SID space. So we could start depleting some of our SID space. I haven't seen it that much. I mean, for instance, Cisco's SID space is 8,175 SIDs per cable interface. I don't really see us hitting that number anytime soon. But really, it could come down to how many devices did you really put on a MAC domain, a cable interface. You get that?
Yeah. No, I get it. I was just curious if I haven't seen SID depletion become an issue, but I do understand with if you're putting all your set-top boxes and your modems on a CMTS, it could become problematic. A number of operators I've seen, they're typically putting set-top boxes, if you reach a certain count on a CMTS, they'll start to deploy those on another CMTS.
Well, you know, another one I forgot about was stale SIDs. I've seen where EMTAs make voice calls, and then when you hang up, there's a T8 timer or one of the T timers that's supposed to indicate, tear down the SID, because it's DQoS, right? Dynamic quality service. So it's a dynamic service add, dynamic service delete. If that doesn't happen, the CMTS might hold on to it, and now you have stale SIDs that are not even being used.
Yeah, so that was something that's a firmware issue, right, or a software iOS issue. That's something that was taken care of.
But I still once in a while see some EMTAs with old firmware that are not sending the timer properly, or maybe it was just some miscommunication. We have a command on our CMTS that kind of like overrides. That says if there's a dynamic service flow, secondary service flow, that has no activity after a user configurable threshold of minutes, the CMTS will tear it down. So we have kind of like a catch-all on our CMTS that if I have, and I usually set it at 300 seconds. So if I have a service flow activity timeout of 300 seconds, so if voice call sets up, tears down, but the CMTS sees the service flow is still sitting there with no activity, no bits per second, after 5 minutes, it'll tear it down.
Yeah, so back to the adage, upgrade firmware on the modems, upgrade operating system on the CMTSs.
Yeah, so let's assume layer 1 looks good, the modem's doing the proper bonding, I'm not having drop packets, my MER is good, my CNR is good, everything looks clean and fine. Then we look at layer 2. Like I mentioned, layer 2 can be between 64, 15, 22 bytes. That's been increased to 2,000 bytes for DOCSIS 3.1. I don't know if that actually is relevant for the GigE ports of the 3.1 modem, or maybe just the wireless part of a 3.1 modem. So I'm not entirely sure like what happens if I go to 2,000 bytes through the modem itself. If it's Ethernet, if it's an Ethernet port. So I don't know if it turns out to be a jumbo frame, or if that's more and it gets fragmented anyway. And maybe that, I'm not really sure at that point. But I do know that if I can do a bigger payload data unit, that the 18 bytes of overhead is less percentage. So that's one way of looking at it. DOCSIS overhead, more than you expect. 6 bytes DOCSIS, 5 bytes BPI plus, 6 bytes of bonding overhead. So there's DOCSIS overhead on every single frame as well. I wrote Powerboost adds a wrinkle to all this. When I start doing letting the modem burst for maybe a peak rate for 10 seconds, that adds a little bit different wrinkle to my speed tests. You know, you see the speedometer go up to 500 megabits per second, and it drops down to 300 megabits per second. So, I mean, Powerboost does give an added perception of higher speed for a certain amount of time. So we can exploit that functionality potentially to get better speed or better reporting, if you will.
So you're saying it adds a wrinkle. I always look at Powerboost as being a benefit overall in improving network speed, customer perception of what they're getting for their the dollar they're paying. So are you saying Powerboost is a bad thing?
Well, it depends if you want wrinkly jeans or straight jeans. Maybe you want the wrinkled look.
I like the straight jeans, but
I said wrinkle meaning maybe I shouldn't use wrinkle. You know, it's a good and a bad. It has pros and cons. The pros, like you said, it gives it better perception of throughput. The con or the wrinkle would be it could make your utilization on your interface look high, even though no one's complaining. So how do you decide when to do node splits? So if you typically had the rule of thumb that once my downstream is 85% utilized, I have to do a node split or add more downstream spectrum, Powerboost could make that appear high all the time, but there's no real justification to do a node split. That make sense?
Yeah. So I understand what
maybe I shouldn't use the word.
I still like Powerboost. I wouldn't take it away.
Layer 3 IPv6 versus 4. IPv6 adds 20 more bytes versus IPv4.
So it's going to add to the overhead calculation.
Yeah, but I mean, what's interesting there is when you do a speed test, it's at layer 3 and above. So basically, if it's IPv6, it's just part of the speed that gets reported to you anyway. So that's at layer 3, so no big deal.
All right.
Layer 3 versus layer 2 reporting. This is what I mentioned earlier, the CMTS reporting versus the speed test site. That could easily be 2 to 10% difference. This is why you'll see a lot of people configure about 10% higher on their CM file than what they actually advertise. So you might offer a 10 meg service, but you actually configure 11 meg just so you can cover this layer 2 versus layer 3 reporting. Kind of like, how do I ring the bell? You know, how do I get the customer to see the speed we're trying to offer and market? Layer 4, I mentioned TCP versus UDP. If you can do UDP, that would be the way to go. If you're doing TCP, keep in mind that upstream speed limitation could affect downstream TCP flows. Over-the-top video is TCP. It's adaptive bit rate, and it's a TCP based. So it will create more upstream acknowledgments and upstream traffic to do more downstream over-the-top video. So Hulu, Netflix, and all that is going to create more ACKs or more acknowledgments and more upstream traffic. Verify utilization, single cable modem speed versus multiple modems. You might have a difficult time hitting your aggregate speed with a single modem because of single modem speed issues. Request grant cycle on the upstream, the CPU of the modem itself. Sometimes it's better to use a handful of modems with realistic speeds to see what the aggregate is for your downstreams. So if you're trying to prove that 4-channel bonding can hit 144 megabits per second aggregate, don't try to do it with a single modem. You know, do like 3 or 4 modems at 30 megabits per second or whatever.
Well, what if you're trying to test a service flow of like 100 megabits per second?
Well, in that case, you shouldn't be doing it with 4-channel bonding in the first place. One of our rules of thumb was make sure your aggregate is at least 2 times the amount of your highest offering. So if you're trying to do 100 megabit per second speed, you might be configuring 110 at 10% overhead, and really you should have like a 220 aggregate pipe. A 220 aggregate pipe would be close to 6 to 8 downstreams of bonding, not 4-channel bonding.
Right. So if I want to do a 100 meg service tier, I need at least 8 channels bonded in a downstream.
I would say at least 6, but we've always tried to keep it an even increment of 4.
Right.
And that makes it much simpler. Because the modems are 4-channel, 8-channel, 16, 24, and 32, right?
Right.
So here's my some of my rules I've been using for capacity planning. That was, I configure 1.1 times my marketed speed, so that's 10% over. That's just to cover my layer 2 versus layer 3 reporting. I would say we might want to start pulling this back and reeling this back to maybe a 1.05 multiplication factor, or maybe even less, and I'll get to why I'm saying that. Downstream to upstream, 10-to-1 ratio. This one has been easy math, and we've been doing this for a while to really cover that TCP, downstream, upstream. We really can start reeling this back a little bit as well. Some people might go the other way and say, I don't know, I might go the other. The reason why I bring this up is when we go 1 gig down, if we do 10-to-1, we'd have to offer 100 meg up. To offer 100 meg up, we need 200 meg upstream pipe. To do 200 meg upstream pipe, you'd need more than 42 megahertz of upstream spectrum. So to work with what we got, 42 megahertz upstream spectrum in the US, you're only going to get 4 ATDMA upstream channels. Beyond that, you get 108. From a 108 aggregate, you could offer maybe 50 meg offering. 50 meg is legitimate and could be used for a 1 gig down and still cover maybe 20 meg of acknowledgements as worst case and still have 30 meg on the upstream for actual upstream flow. Now, the pitfall to this 1 gig by 50 is marketing. If you offer a 300 by 30, you really should start pulling back the 500 and go maybe 500 by 40, then 1 gig by 50. If we keep doing the 1-to-10 ratio of downstream to upstream offering, we're kind of pigeonholing ourselves. Or
1 gig by 100.
Yeah, but I'm saying we need to start pulling that back so people aren't getting the perception that every time they upgrade downstream, they're going to get an upgraded upstream, because we're hitting the brick wall on the upstream.
Right.
So I really think a 1 gig by 50 makes sense. A 500 by 40 makes sense. Maybe a 300 by 30 is the last time I do a 10-by-1 ratio. Some people would argue that with 1 gig down, maybe you should have more than 100 meg up. Some of the things that help us on the upstream is ACK suppression. But we find that when we have a lot of downstream flows that are kind of low speed, like 5 to 10 to 15 megabits per second, you won't get much ACK suppression happening anyway. So if you had a 3.1 modem in your house, or even a 3.0 modem in your house, and you had Xbox and 5 kids doing over-the-top video, and you're doing DVR of 2 shows and you're watching a show, there could be 10 different flows happening. Each of them might be 10 meg apiece. So that's 100 megabits per second. When I do 100 megabits per second with one flow, my ACK suppression drops my ACK from 2 meg upstream to about 700 kilobits per second upstream. So ACK suppression is great. But when I do 10 flows at 10 meg apiece, it's 100 megabits per second aggregate of speed, I don't get that ACK suppression kicking in. So you end up with about 2 meg of upstream traffic to support all those low speed flows. I'm saying low speed, 10 meg is kind of low speed nowadays, but
that's a relative term.
It is, isn't it?
10 meg low speed.
So the number 3 was Powerboost, and Powerboost was great for low speed tiers from DOCSIS 2.0 modems. But I really think that if you look at my point number 4, I could exploit Powerboost to bypass rule number 1. So I really think that once I get to 1 gig down or even 500 meg down, I don't want to do a 10% over provision, because 1 gig, 10% over would be 1.1 gig provisioning. You're offering 100 megabit per second over provisioning just to cover your layer 3 versus layer 2 reporting. Well, maybe I can just do Powerboost for 6 or 7 seconds, and that can kind of cover my layer 3 versus layer 2 reporting, because the only time I'm reporting is when people are doing speed tests. So why not use a peak rate TLV and let the Powerboost take care of it? And I actually have some diagrams of Powerboost coming up. I did some Powerboost with DOCSIS 3.1. Oh, sorry.
New slide.
Yeah, I hit enter. I thought I was doing a slideshow. So one of the things I already talked about was aggregate speed should be 2 times your highest offering. Oversubscription is fuzzy math. I mean, really, we run these numbers trying to give people an idea of how to oversubscribe. So what I've come up with was if your aggregate is 2x, meaning if I have 100 megabits per second pipe and I'm offering 50 megabits per second service, you might be able to do a 25 to 50 to 1 oversubscription. When your aggregate is 4x, you could probably get away with 50 to 100 to 1 oversubscription. If aggregate is 10 to 1, you could use a 100 to 1, and that's kind of where we used to be back in the old days.
Now what is the? I'm not following the aggregate number. Can you explain that a little bit?
So if your aggregate pipe size, and let's say it's a 8-channel bonded modem, so the aggregate for that 8-channel bonded modem is about 288. So from that 8-channel bonded modem, if you're trying to offer 50 megabits per second, well, 288 divided by 50 is about 300 divided by 50 is 39. It's about 6x.
Right.
Right.
I got the X now. The X.
So basically, all 8-channel modems that are offering 50 megabits per second, you could probably afford to put in there. We came up with about 6x. So 6 modems could operate simultaneously. If you oversubscribe by 50, 6 times 50 would be 300 of those modems. So if you had 8 downstreams and you offered 50 megabits per second, 300 modems could share those 8 downstreams.
Right. Now this is good fuzzy math, though. I like the way you look at the aggregate and apply that to an oversubscription model.
I mean, I think kind of the bottom line there is just like Erlang's and voice capacity planning. When the trunk is bigger, you can oversubscribe more.
Right.
And that's basically what you're saying. The trunk is 10x, you could oversubscribe maybe 100 to 1. Now, some people might cut all these numbers in half. So, I mean, it is fuzzy math.
Yeah, well, it's always up to the operator to decide how much where their threshold is to say, I'm comfortable with this oversubscription number. If they want to be more conservative, they reduce it.
Yeah, and I always say this is a starting point, right? It's a starting point, and then you actually track utilization, which is point number 9. You know, you start out with your assumptions, and then point number 9, you monitor actual utilization. Point number 10, that's kind of that could be a touchy subject, but it's still the old rule of thumb is, 10% of your users are eating up 80% of your spectrum or 80% of your capacity. So you do have some people that are abusing it. So by controlling them or maybe forcing them to slower speeds once in a while, putting them in the penalty box, whatever you want to call it, you could have better quality of experience for everybody else by controlling abusers. I mean, we got to admit, this is a shared medium. We are sharing it, which is the baseline of our oversubscription. And this is how we make money, by oversubscribing it.
At the end of the day, we're here to make money.
Yeah, I mean, it's true. So for all those kind of capacity planning, I also had 10 points to ponder. That was basically stuff we've been talking about already. I kind of bring up a few things here, and Brady, I can give you a copy of these slides and people could download them. I don't know if you want to put them on your website later on.
Yeah, I can do that.
So I don't want to go through every one of these, but looking at Powerboost, this was the original trademark name from Comcast, and other people might call it something different. And some MSOs have actually, I think, got the naming rights with Comcast to call it Powerboost. On Cox Communication, they call it Powerboost as well. Here was a downstream Powerboost where I was utilizing Powerboost to not have to over provision this modem 10%. So I said, well, I'm going to offer a 500 meg service. I'm going to configure a peak speed of 600 meg, a max rate of 510. So I'm only really over provisioning 2%. But I did a peak rate of 600 meg, and I did a 70 megabyte downstream max burst, which equated to about a 6-second power boost.
Now, did you run a speed test on this to see how it actually looked on the speed test site?
Yeah, and this is what you're seeing right here. Is it was from the bite blower? I don't know if you're familiar with.
From Accentus. Yep.
And I was doing DOCSIS 3.1 showing offering a 500 meg service, but really provisioning 510 with a peak rate of 600, but a 70 megabyte downstream max burst. That right there equates to about 6 seconds of power boost.
Yep.
So from an end user's point of view, they would see close to 600, maybe 580, but they're only paying for 500. So they're happy.
Yeah, absolutely.
Well, if I want more time, I would just make this downstream max burst more bytes. I might do 100 megabytes and get 10 seconds. Really, the amount of time the power boost is related to how high is that peak above my max rate. Like this area, can you see my mouse moving?
Yeah, I can.
Yeah, if you looked at this area under the curve right here, that would be like saying that's 70 megabytes worth of data. But if I said 100 megabytes and kept that same peak, that would end up extending it further in time. If I change the peak up to a higher peak, this would have to pull into a shorter amount of time to have the same area under the curve.
And what controls the peak again?
That's an actual setting. It's a peak rate TLV in the CM file.
Okay.
Yeah, that's an actual setting in the CM file. That was added with DOCSIS 3.0, and then I believe it was backported for DOCSIS 2.0. Maybe only with service class names in the CMTS.
Yeah.
But it's a DOCSIS 3.0 peak rate TLV. I even said, you could do this on the upstream as well. Not many people know this, but you could manipulate this setting in the CM file called max upstream traffic burst. So what I did is I set a 10 meg service. I set it for a 15 meg peak rate with 2 megabyte upstream max traffic burst. I got about a 3-second power boost on the upstream. So this is just showing functionality of power boost on upstream and downstream.
Right.
Continuing on with my downstream points, we talked about the TCP being a problem. More frames, more CPU. Let's see. Netflix over the top video, adaptive bitrate stuff. That's going to cause a little bit extra overhead.
And the ACK suppression,
upstream acknowledgements.
That's all automatically turned on. That's not something that someone needs to turn on or we can really change. That's all done in the firmware.
Correct. Even when you do downstream TCP testing, because the TCP window can automatically adjust, I wonder sometimes, does ACK suppression affect my downstream TCP flow stability? A lot of times you'll do a TCP flow or test and you'll see it look like a sawtooth because it's ramping up. Then it could be ACK suppression, maybe drops one ACK, but that ACK suppression, really that one ACK really was 4 ACKs.
Right.
So now your downstream TCP says, oh, I was trying to do 10-to-1 downstream TCP windowing, and they had to drop back down to 4. So now your speed drops. Or could it be, what if I have power boost? If I do power boost at the very beginning, does that affect my over-the-top video setup because of adaptive bitrate? And what if it's a TCP flow? Well, normally when you do a speed test, the speed test is done by the time power boost is done. So maybe that's not such a big deal. But when you do long-term TCP tests, you could see a sawtooth type of reaction, right? I mean, that's why I say if you're doing a speed test, UDP would be the way to go. TCP can have a lot of variables that affect your results.
Mm-hmm. Yep.
As far as upstream goes, the DOCSIS protocol really screws me up with DOCSIS 2.0.11. You have to do a request grant cycle. So this request grant cycle of a modem making a request, CMTS sending the grant on a downstream MAC, that can take a long time. So going to DOCSIS 3.0 with continuous concatenation fragmentation, it's called MTC mode, I get much better speed. So there's a few tweaks I need to do to get better upstream speeds when I look at single modem speeds.
Yeah, so actually, I want to mention that, John, because that was something that you had taught me that I did not realize, that even if you're not doing channel bonding in the upstream, that it's important to enable MTC mode in the upstream because it enables that functionality you just mentioned, continuous mode.
So, yeah, even if you don't make an upstream bonding group, at least the Cisco CMTS has single channel default bonding groups. So a modem that comes up in one channel MTC mode, that modem will have better per modem upstream speed than a 2.0 modem. If that makes sense. Yeah. Still single channel on the upstream, but it
didn't make sense to me when you first told me, but it did make sense to me after I did it, and I got better performance. So.
And so downstream speed is a lot of things that affect my traffic. Upstream speed, same thing. At the very bottom, I mentioned, mod profiles, channel width. Bigger pipes are always better. Looking at some throughput numbers. This was just for DOCSIS 2.0, or single carrier QAM, DOCSIS 3.0, DOCSIS 2.0, single carrier. Most times, I'm telling people the real usable throughput of a downstream channel is closer to 36. It could be 37.5 if it was secondary only. But when you do primary for 2.0, 3.0, and modems to lock on to that downstream, then you have downstream maps. And the more upstreams in a cable interface or more upstreams in your MAC domain, the more maps you have to send on the downstream, which creates more overhead. Upstream, now we're looking at 64 QAM, 6.4 megahertz on the upstream, which equates to about 27 megabits per second usable rate. Increase my speed, more compression. Is it H.265? Does that sound right? Is it H.265 or just H.265?
H.265.
Okay, I couldn't remember if I had it right or not. I mean, that's trying to take your compression another level above MPEG-4. So, we're trying to do analog reclamation. Now we're trying to do digital reclamation where we're getting rid of MPEG-2 and trying to go to MPEG-4 IP video. But now when you're looking at, if you're doing 4K TV, we need even better compression. So H.265 gives better compression. But now we're sending even more bytes and bits for 4K TV. So it's funny. It's like we seem like we get better compression, but we keep coming out with higher definition. So they kind of offset each other all the time.
Yeah,
so
8Ks are coming.
Yeah, so we're right back to almost 6 megahertz of spectrum needed to do, say, 4K TV, one channel, because it's speed that might be needed. Yeah. And it obviously depends on how much compression and everything else is going on. I don't think it's quite that bad, but you sort of get the idea. Have you heard of any speed requirements for 4K TV?
Well, I mean, for 4K TV, the original guidance from Netflix was about 25 megabits per second, but now they're improving the compression, where I think they're down around 12 megabits per second for the 4K TV.
That's a big improvement.
It's a huge improvement, but they are saying it's going to be dependent upon the amount of movement in the picture. So it's really high. If it's really high action, then it's going to be. It is a dynamic. It's a variable bit rate. On it, so.
It's like, what kind of movie are you going to watch with 4K? I mean, I'm going to want to watch action flicks with 4K.
I want to watch CNN all day long on 4K. Talking heads.
Yeah, and pretty soon, the actors are going to say, "Hey, can you make my face SD TV?"
Yeah.
Can you do standard definition on my face and just high def on everything else?
Yes.
So, I mean, increasing our aggregate speed obviously is going to get us better speed. DOCSIS 2.0, 3.0, 3.1. 3.1 is where we're going. Downstream, upstream will be coming down the road, but with limited upstream spectrum, I don't see 3.1 upstream really being a push for quite a while. Unless we go 5 to 85 megahertz, then it very well could be. And some systems I know are going to 85 megahertz in the upstream. So here's my high-speed recipe. Layer 1, full upstream downstream bonding, proper CM file settings, wired connections. So not just one wired connection, maybe multiple wired connections. No drop, delay segments, frames, or packets. So make sure my physical layer is good. Layer 2, always test with the biggest frames possible. Layer 3, if we do IPv6, I don't know that there's any problem there. The only issues I've seen so far was when I was looking at voice capacity on my CMTS, we have a special mod profile for voice called AUGS in the mod profile. It's a burst, AUGS. And I have it optimized for a 232 byte voice frame. Well, it turns out that voice frame now is 252 bytes because the extra 20 bytes of IPv6. And if I do BSOD, business services over DOCSIS, with a 4 byte VLAN tag, it could be 256 bytes. So there is some manipulation I've done to my AUGS burst to get a little bit better efficiency on my voice packets. So that kind of comes into play in my voice testing. Test with intended speed. Here, what I'm trying to say is you don't want to take a modem that you want, I don't want to say this. Say you're testing 10 megabits per second on the upstream, and you blast the modem with 40 megabits per second into the modem. That modem has to buffer that information, try to concatenate it, store it, send it, make a request, and get a grant, and keep sending and concatenating it, and then sending it and buffering it. I've found that sometimes modems get inundated with too much traffic and kind of like choke on it. Sometimes you're better off, if you're trying to do 10 megabits per second, inject 11, or start with 5 and then work your way up. Don't just blast the modem with speed and have it wide open. So if I do 50 megabits per second on the upstream, I might test with 50 or 55 or 60. But I'm not going to try to blast it. And oh, by the way, if you ever reboot a modem, make sure you turn off the traffic generator. You know, sometimes that traffic generator blasting the Ethernet port of a modem, when it's trying to reboot in the background, it just kind of hangs.
Yeah, it's not going to reboot. You can't get its DHCP and request through.
Yeah, so a lot of times these traffic generators might be just blasting traffic. It's not really a speed test site, right? It's just a traffic generator. Layer 4, test with UDP if you can. If you need to test with TCP, maybe you should do multiple flows or multiple cable modems. Some of my checklist was highest offering should be half of the aggregate. So the aggregate pipe should always be 2 times your biggest offering. Use Powerboost wherever you can, maybe even exploit it for those higher level speeds to get rid of that 10% over provisioning. Self-healing features like load balancing, resilient bonding group, dynamic modulation. Place your DOCSIS 3 on PLC in the best spectrum possible. So you should know what your spectrum looks like. Manage fair use of the network with maybe subscriber traffic management, byte counting. Find out who your heavy users are. Use IPDR. Monitor traffic load. That one's interesting too, because I've had people have a large rolling time average window, and it affects their load balance, meaning if it's really large window, the load balance looks perfect, but it's not. So if I had a 5-minute window, you could have 50% utilization, but it's really not 50%. It was 50% in 5 minutes. So every minute it could have went 100%, next minute 0. Well, now at 5 minutes, it's 50%. So really a little bit more granularity in my rolling time window would be a little bit better. I've been setting my load interval in my CMTS to 30 seconds, which was the lowest setting I could. And it gives me a little bit more up-to-date readings for my load balance utilization. Monitor your modem states, make sure the modems are doing what it's supposed to be doing, and utilize periodic speed tests. That could be the built-in FTP functionality in some of the newer 3.1 or 3.0 modems. I know Comcast and others might be using something called Banana Pi or Raspberry Pi, a small, what is that, Brady? It's a small.
The Raspberry Pi, right? Is that?
Yeah, but I think they're using another one called Banana Pi.
I haven't heard of the Banana Pi before.
Yeah, so it's a small,
yeah, little tiny Linux hardware board, little tiny computer.
So you could like attach it to your modem in, say, I don't want to say a user's house, but maybe an employee's house.
Yeah,
right?
a friendly user.
Yeah. That way you could do a speed test. But if the modems have a built-in FTP server, why not just use that? So instead of attaching an external device to do a speed test, why not use the internal FTP? Now, I'd have to make sure if I'm doing.
Yeah, so in the DOCSIS 3.1 spec, part of the P&M capabilities is that every cable modem will have its own ability to do a speed test.
And I think that's part of it, right? The built-in FTP server?
Yeah. Yeah, it's a TFTP file transfer that allows us to do it.
Okay. Some other points here: understand the theoretical rate before you test. Math is just my starting point. Bigger pipes are always better. This bullet point here, just because you have more speed doesn't mean you have better quality of experience. Because what if you have latency or jitter sensitive services like gaming? So I gotta wonder if I have a gaming service that's say 5 megabits per second, would I get better latency or less latency and less jitter if I push that service flow to a 4-channel bonding group versus a 24-channel bonding group?
Because you're not striping across 24 channels, you're only striping across 4 channels or 8 channels.
Yeah, because then you got to resequence the packets, everything has to come in. You would think, it's faster speeds or everything should be coming in very, very fast, and resequencing and all that. But it remains to be seen if this is an issue or not. But I've seen it happen with voice already, where a downstream voice call, when you do all the overheads, only about 110 kilobits per second. But if you stripe it across 8 downstreams, you could get voice jitter and latency. So you get voice quality issues.
So basically, the more channels you have to sequence or stripe across, that resequencing is that increasing latency and jitter?
Potentially, yes. So, I mean, it's if we look at how voice reacted, maybe other flows would react better as well, like gaming flows that you're more, you want to see the snappiness of, you're shooting a gun or whatever's going on in your game. You don't want any latency there.
Or even,
so would it be better?
Even non-managed service voice services like Skype or FaceTime or things like that, I would imagine it would impact.
Correct. And then even I mentioned at the beginning, we don't bond upstream traffic that's scheduled. Well, Skype and bondage is not scheduled traffic. It's best effort voice. So that stuff would get bonded depending on like how it gets put in there. So there could be some latency and UGS is unsolicited grant, so you don't make a request; it's unsolicited. But VoIP and Sconage makes bandwidth requests that could have contention.
Right.
So the more bondage and Skype you have, the more contention and collisions you could have. So you could drop packets that have worse quality of experience. But I mean, that's a good thing for cable operators, right? We're trying to push our own UGS flows and not have people use bondage and Skype. Well.
Yeah, the reality is people are using it. And things like FaceTime and stuff like that. I mean, we have those services are growing, and I think we're going to see a lot of usage of that. And they're just simply not going to be something that a cable operator can offer easily as a managed service, because they grow outside of the network. They go from a wireless network onto the cable network, and then off the cable network.
Correct. So my last slide basically was saying, ounce of prevention with a pound of cure, meaning be aware of potential ingress sources on your spectrum. So either stay away from them or just be cautious. Like, where do you place your PLC for a DOCSIS 3.1? Reassess your spectrum. Someone the other day asked, with all this downstream channels, video, DOCSIS 3.1, do I even need to do downstream sweeping anymore? Or is it really like a sweepless sweep? And where I see actual sweep insertion still being relevant is validating the spectrum that you never validated before. Meaning, if I'm going to go from 860 to 1 gig, you're going to have to validate your plant's going to be able to go from 860 to 1 gig without huge roll-off from water in the taps, suck-outs. And what if you decide to go to 1.218 gigahertz, DOCSIS 3.1 spec? So now you're going to maybe have to inject carriers there before you even decide to put a DOCSIS 3.1 OFDM channel in there. So inserting sweep points at that upper end where we've never even seen what it looks like is going to be a necessity. Be aware, it could be we use the full bandwidth capture of the modems as well. And maybe we look at the noise floor. But I don't know if that would strictly replace a sweep type of response.
And going to 1.218 gigahertz is actually a really valid application, because one of the reasons the DOCSIS 3.1 spec is allocated out to 1.218 gigahertz is because they believe that if you had a 1 gigahertz plant now, that we can go well beyond 1 gigahertz with DOCSIS 3.1. DOCSIS 3.1 would support that, so going beyond it is something we can do. It might be a lower order modulation. It might not be 4096 QAM. It might be 1024 or even 512 QAM. But those subcarriers will go out there. They might be rolling off, but sweeping out beyond that would tell us, what's the roll off? How far out can we go? Maybe it's not 1.2. Maybe it's 1.1 or 1.15, something like that. But being able to support frequencies beyond 1 gigahertz with existing plant gives us a lot of capability to add capacity beyond that. So those are really great opportunities. And to your point, that's an opportunity to maybe sweep out beyond that and see, what can we do in those areas? How much spectrum can we support before we actually deploy it? Or maybe cable operators are just going to start putting 3.1 out there and see how much roll off is is there with a 3.0 or 3.1 modem and see what the modulation is.
Yeah, I mean, it could be a costly proposition, but then again, maybe they just activate the spectrum out there and don't even put modems on it yet, right? Maybe you just activate.
Right. Yeah, you're gonna see what the roll off is one way or another. So you can do it with sweep, or you can do it exactly, because it gives you a nice flat spectrum. If it's not rolling off, you're gonna see the roll off in the spectrum itself.
Yeah, so. And then by going to each modem that has a full bandwidth capture, you're getting basically an end of line report everywhere you have a modem.
Yep.
And the other reason we want to go out to 1.218 gigahertz is because the upstream might be eating into my downstream. So if I go from 42 to 85, I just ate a few channels out of my downstream. If I go from 85 to 204, you really ate into your downstream.
Yeah, so we got to make some shifts and increase our frequency spectrum. So, all right, you wrapped up on that presentation?
Yeah, it's what else? I think that was basically it. I mean, you mentioned ANGA at the beginning of today's Google Hangout. At ANGA in Cologne, Germany, I was on a panel that I thought was kind of interesting. Is most people say if it's a greenfield deployment, why not just do fiber to the home and do EPON, GPON? And one of the people in my panel, they were doing a complete rip out and overhaul, and it wasn't quite greenfield, but it sort of felt like it. And they decided to do a remote PHY. And so even though it was kind of a complete rip out, the remote PHY architecture and solution still has a lot of cost benefits over a complete GPON, EPON solution. One of the things, it's funny, we used to say last mile, last mile, last mile. Now it's not last mile, it's last 100 feet. That drop cable or twisted pair into the house is one of the biggest hurdles, I think, that's going to be tough to overcome as far as cost goes. So running remote PHY or fiber node plus 0 amplifiers, almost getting rid of all the coax except for maybe the drop cable, that's going to be something in our future for a long time, I think. If it was a true greenfield, you probably would do fiber everywhere and be done with it. But if it's you're going to a almost, I don't want to say a brown field, but it's in between brown and green, whatever that is, hazel. I don't know. You're basically ripping out everything, going fiber as deep as you can, trying to get coax limited. You now can go to 204, 254 split maybe. I'm afraid of higher upstream spectrum because of loss in coax and temperature effects. But if there's less coax, not a big deal. If you do digital fiber with remote PHY, you don't have laser clipping. So there's some functionality there and feasibility of doing deep fiber, higher upstream splits, more speed, more upstream speed, more downstream speed. And I think that's where things are kind of going. All right. Good.
Good stuff. So yeah, you can stop sharing your screen there. It's been flickering the whole time, driving me nuts, man. So, but good stuff, good information. If you send me the PowerPoint presentation, I'll upload that to the site along with the link to the Hangout and also the podcast. The audio podcast will be shared later. And otherwise, excellent material, John. Appreciate your time.
How do I stop sharing it? I don't even know how to stop sharing.
Yeah, you stop sharing it. So, all right. Well, thanks for everything. Thanks.
That's the longest hangout we ever had.
Yeah, absolutely. we killed a good hour and then some.
Yeah, I'll send you the slides so you can put it on your website.
All right. Thanks, sir. Have a great weekend, and we'll chat soon. Take care.
Yeah.